Welcome back to ECE 501B. Homework number 3 is due on the day that we meet next time. That's Monday the 23rd of September. Exam number 1, that's 2 weeks from today, October 2nd. Just as a reminder, hopefully that's not scaring you too much, but I did want it to stand down a little bit. That's why it's in red. Hopefully you'll start to prepare for that, and the material should be consistent with what we've been working on relative to the homework sets that are being assigned, and we'll probably have a 4th homework assignment due prior to exam number 1. Today what I want to do is just kind of get us back on the same page by recalling or recapping what we had talked about last time, maybe in several different locations in the lecture. But right now, let's then talk about or begin the discussion with the same example, but compare this null space of T and the range space of T relative to that example. And that's actually going to hopefully motivate theorem 3.4, which is comparing these dimensions. It's really saying the dimension of your domain can be separated into 2 pieces, or 2 different dimensions. The dimension of the null space of T, which if it's trivial, that will be 0, and your entire domain's dimension will be equal to the dimension of the range of T of your operator. Now, what we want to do then is once we have that theorem, we can look at some corollaries which deal with injective maps, surjective maps, and dimensions. Then we'll bring all of this back to where maybe you've been thinking about all along as matrices. The matrix representation of these linear maps. That's maybe how you've been thinking about it to try to get a concrete example all this time when we're talking about a range space, null space. If you've had linear algebra with matrices, you've already seen these subspaces, I hope. And there's actually 2 others that are orthogonal complements to these 2, but these are the 2 that we're talking about now, the range space of T and the null space of T. And those 2 up here in the earlier part actually are dealing with subspaces within 2 different vector spaces, the domain and the codomain. Once we have these matrix representations, then we'll start talking about invertible maps, which really means that the maps have to be both injective and subjective, and we'll see what that translates into in terms of a matrix description. What does that mean? We will then talk about isomorphic vector spaces. Hopefully we will get that far. I don't know if we will. Maybe I'll have to provide another supplemental lecture, and you can watch that at your leisure. If you're having trouble sleeping, I'm assuming you're watching these videos. And that way, if you just can't get to sleep some night, you can plug that in or pull up YouTube, and it'll put you right to sleep. It's better than coffee? Oh, I didn't know that. So here's our example. Here's our linear map, T, that's going from a 3-dimensional domain, R3, into a 5-dimensional codomain. And we sometimes say our domain is V and the codomain is W. So that's the parenthetical relationships here. This is the example that we were using during last lecture. This should be the same. It's just now I'm using it to sort of motivate theorem 3.4. Here is our linear map, and we found last time, maybe we didn't find this directly, but you could do the row reduction on a matrix relative to this linear map and find that a vector, a 3-vector, equaling -2, 1, 1 is actually in the span or is forming the null space of that linear map T. If you pick an x value, a y value, and a z value with this relationship among their values, minus 2 times x, 1 times y, and 1 times z, if you're living on that line in this three-dimensional space, you plug those values for x, y, and z into this map, and you'll get the zero vector. That's all that's saying. The vectors on that line will map to 0 in R5. So this is now the vector, the three-component vector. This just represents a line which is one-dimensional, but it's in the three-dimensional space. Our domain is three-dimensional. But there's only one line in that three-dimensional space that if you pick a point on that line, it will map to the origin in the codomain's zero vector. That's all that's saying. And we, I think, introduced that last time. Which means that T is not injective. There's not a one-to-one connection between points in the domain, or vectors, I should say, in the domain and vectors in the codomain, because we have a non-trivial null space. That non-trivial null space is of dimension 1. And that dimension 1 null space is just a line, so it's a subspace. It's a line going through the origin. Null space is a subspace. We talked about that last time in our three-dimensional space. Then I just thought, you know, why don't we just remind ourselves what it means to be not injective? And that means that we can take 2 points in our domain and they can actually map to the same point in our codomain. Reminding ourselves, U1, let's just pick that number or that vector, minus 2, 1, 1, and then if you plug those values into the linear map, you'll get all zeros in R5. You'll go to the zero vector. What if we pick a different vector in our domain, V1, that really just has x equal to 1, y equal to 0, and z equal to 0. And if we went back to our mapping, our linear map, we would simply substitute 1 for x, 0 for y, and 0 for z, and we would end up with -1, -1, 1, 2, and 1. That would be the result of operating on that 3 vector, 1, 0, 0, with this linear map. And that's all we're saying here. T of v sub 1 maps to the point in this 5-dimensional codomain, -1, -1, 1, 2, 1. Since this map is not injective, we have a non-trivial null space, we could actually create a new vector in our domain, let's call it v sub 2, that could be a combination of these two. And that's not going to be the same point as v1. I hope you can see that. If we add v1 and u1, we're not going to get the same value, are we? v1 plus u1 gives us a vector x equal -1, y equals 1, z equals 1. And this v2 is not the same as v1. But now, what's going to happen when we operate on v2 with the linear map t? We will get t of v1 plus t of u1. And we already know what those are. Or we could just do it directly with t of v sub 2, and remember what that was. That means replace all the x's with -1, and that's what this column represents in the t of v sub 2, plus 1 everywhere y was, and sometimes y was a y, sometimes it was a 2y, sometimes it was 3y, so we're adding the linear combinations of y, Then we add in the z's. That was just how the map was defined, and we end up with this location in our 5-dimensional space. And that should look very similar. That's exactly where V1 was mapped through that same linear transformation. And that shouldn't surprise us. But what that does say is that since T has a non-trivial null space, we can take two different vectors in our domain, V1 and V2, process those through the linear map, get to the exact same location, maybe a W1, but yet V1 and V2 are not the same. And that's what we meant by something being not injective. To be injective, then T of V1 would generate some vector in the codomain. T of V2, if it was different from V1, would get you to another place in your codomain. That's what we're meaning by injective. It's a one-to-one relationship between our domain and our codomain. We can also look at the range space of T, and we did last time, and we found that if we look at what could happen, and one way to do that would be to go back to our original map, linear map, and replace this with three different vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. That'll give us three vectors. Well, there was actually some linear dependency among those three vectors. We eliminated that and said, oh, you know what? Those three vectors were dependent on two directions, essentially. And these are two directions that span the range of that linear operator. And these are the only two directions that you can get to from any vector in the domain. Some vectors in the domain will take you to the origin, won't they? Those are in the null space. These vectors are going to map out the entire range space. So this is obviously not filling up all of R5. It's just filling up 2 dimensions in that 5-dimensional space. So it's not surjective, is it? Surjective means we can cover the entire codomain with our range space of our linear operator, and that's not happening. In particular, we can see that there's 2 linearly independent vectors that we can use to span the entire range space of T, which isn't very much relative to a 5-dimensional space. Consequently, our dimension of the range of that linear operator is just 2. And what was the dimension of our null space? We just had a line, didn't we? So it was 1. And what was our size of the domain vector space? V. 3. 3 is equal to 1 plus 2, isn't it? That's the observation. Dimension of our domain, V, which was R3, is 3. And that, in this example, is equal to the dimension of our null space of T plus the dimension of our range space of T. And remember where these are living. Null space of T is a subspace in what vector space? V or W? It's in our domain, isn't it? It's V. So that one we feel okay about, but now this range space, what's that a subspace of? W, our codomain. So that's a subspace in this 5-dimensional. But what you can think, if you have had some linear algebra, is this is really the dimension of your null space plus the rank of the matrix if you had this linear map as a matrix. the rank of a matrix is the same as the dimension of the range space. It's also the dimension of the row space. You have the same number of linearly independent rows in a matrix as you have linearly independent columns. I mean, we haven't talked about that, but that's really what you have in this setting when you're dealing with matrices. And this is not unique to that particular example. It's not a coincidence. It's actually a theorem. And that's where we stopped last time. We stopped with this theorem. We said theorem 3.4, so we're not very far into chapter 3. We need to move along. But in chapter 3, if we have a finite dimensional domain, so an FDVS, that's kind of cute, isn't it? FDVS, fire district of, I don't know, somewhere, VS, and a linear map T that's mapping V into W, a domain into a codomain, then we have this relationship among the different parts of that linear map. The linear map in our example was taking a three-dimensional vector space into a five-dimensional, and it wasn't even using up all of that volume, was it? It was only filling up a two-dimensional space in R5. And we had a one-dimensional piece of our domain that would map into the zero vector of W. But given a finite dimensional vector space V as our domain, then we know the dimension of that domain, that was 3 in our example, is equal to the dimension of our null space of the linear map plus the dimension of our range space. Let's see if we can work our way through the proof of that theorem. First, let's just assume we have a number for the dimension of our null space. So let's just take the dimension of the null space of T to be M. Once we have that fixed number M, then we can actually fill that up with a basis, a set of bases that will span the null space of T. Now then there is a basis let's say U1, U2, and that basis can only be M big in terms of vectors. Now we have a basis set. And that generically is not the same as the size or a basis of our original domain, is it? Typically, the null space is a subspace within the domain, meaning this is not going to be a basis for V or our domain, and we need to build it up. But we have a theorem to do that. So we can use our theorem back in chapter 2, which said that we could complete a linearly independent set of vectors and fill up and build a basis. We could just add more linearly independent vectors. So from theorem 212, we know we can extend this basis on the null space of T to a basis of V by adding the necessary number of vectors, by adding however many vectors we need. So let's just let that basis now and now I want to distinguish between Michigan and Nevada. Now I started with Michigan vectors for the vectors that were spanning the null space of T, and then I simply built up or added on to that another set in Nevada to create a basis for the entire domain. So that's the dimension of V. And that now tells us what we're saying the dimension of V is. It's M plus N. Now, to complete the proof, we already know now the size of V. We know the size of null space of T. We just have to see, can we show that the range space of T is little n? That's what we have to prove. So to complete the proof, we need to show, or we must show, that the dimension of the range space of T is equal to n. That's what we need to do. So now let's play with this linear map T and have it operate or work on some generic vector V in the domain. So let's take just any arbitrary vector V in our domain. But now let's rewrite V in a special way. Let's write it as a linear combination of our basis vectors. We can do that, right? If V is coming from our domain, then we can write that as a unique combination of our basis vectors. Let's just say that that V is now A1, U1. I need to stick with the right A2, U2 plus A sub m, U sub m, plus, let's say, B1, W1 plus B2, W2 up to B sub n, W sub n. Because the U's and the W's were our basis for our domains, capital V. That was our domain space, and we now have built up from the null space basis, we've added vectors W1 through Wn to complete the basis. Well, let's now just look at this linear map from, or apply the linear map T to V. So now we have T times V. But what is that going to be? We can actually not write down a lot of that because we know T operating on U1 is going to be what? Remember what the U's were? They were in our null space, weren't they? So all of the T's times the U's are going to go away. They're in the null space, and all we really have to worry about is T operating on the W vectors. So TV is actually going to be B1 TW1 plus B2 TW2 plus all the way down to B sub n T W sub n. And that's because all of these TU sub L's are equal to 0, and that's the upside down A for all L's between or living in this set of integers 1 through n. Now that we picked a v that was just a generic v, and w now was spanning the rest of the domain that wasn't getting mapped to the origin. So all of these w's, when operated on t, actually say what their result is going to do is cover the range of t, right? That's going to give us all the possible vectors that will result from this linear map T. The T W sub j's span the range of T. And that was because we picked V to be any arbitrary vector. Any TV can be expressed as a linear combination of these W vectors. Those were spanning the rest of our domain set. And by definition of the range is just those set of V's such that TV is, or the result of operating on that any vector V in the domain maps into or gives you the range of T. That's by definition of the range of T. So now, let's just look at a generic linear combination of the mapped W vectors. So let's now consider a linear combination of these T, let's say, Wi's such that the following happens. Now let's just introduce some new coefficients. C1 T W1 plus C sub 2 T W2. Let's pick these C's such that the linear combination of these n vectors that are mapping the W's through this linear map T, that linear combination of vectors by the choice of the C's is equal to 0. So there's some linear dependency among these vectors T, W sub i's. But if this is the case, what do we know? Knowing that T is a linear map, we can push those constant coefficients C's through the linear map so that they're combining with the W's directly. And we can factor the T out of all of those. This line right here that I've written can also be said to equal T times C1W1 plus C2W2. That's true. If the top line is true, the first blue line, then this second line is true because T is a linear map. Well, now what do we know? Now we have t operating on a vector, mapping us into the origin. Where do we know that vector must live? It needs to be in the null space of t. That's by the way we define the null space. So this set of vectors, this linear combination of w's, is in the null space of t. But now let's keep going back. What else did we know? We actually picked a basis for the null space of t, didn't we? We said the null space of t is spanned by u's. Well, if that's the case, and this vector of w's is in the null space, then we can rewrite that as a linear combination of these u's. Meaning now we can say, okay, now we can expand this vector, or write this vector in terms of the basis for the null space of t. Meaning we can now say that we could say, okay, C1W1 plus C sub 2 W2 plus C sub n W sub n can be written as a linear combination of u's, which is, let's say, D1 U1 plus D sub 2 U sub 2 D sub m U sub n. But what do we know about the u's and the w's? We started with the u's, didn't we, at the very beginning? We started with this set of u's that formed the basis for the null space of t, which is a subset of the domain V. We built up a basis for the entire set V by the choice of these w's. And those, by definition, needed to be linearly independent from the u's. Well, now if we simply pushed one of these sets of linear combinations to one side or the other, that's going to be u's plus w's equals 0. But we know they're linearly independent, and the only way that linearly independent vectors can sum to 0 is for what to happen? All the coefficients have to be trivial. They have to be 0, don't they? So let's write that down. This relationship now says that, or what I just said, but all of these vectors, u1, u2, u sub m, w1, w2, w sub n, those are linearly independent by construction. Is that okay to say it that way? Thus, all of those C's and D's have to be identically 0. Well, if that's the case, and I keep changing the index on my C's and W's and U's and everything, but I hope you get the idea. The C sub J's, if those are all equal to 0, remember what we started with? We picked a linear combination of the w's that equaled 0, and they were all combined with the c's. So now this c, and actually it was the tw's, wasn't it, that we started with? If this is now equal to 0, and now we know all the c's are equal to 0 for this to be true, what's that tell us about these vectors? They're linearly independent, aren't they? So now we know that those vectors t, w sub j's are linearly independent. But we already just earlier realized that those TWs also span the range space, didn't they? By definition. So now we have something that spans a subspace, and those vectors are linearly independent. So now they form a basis for that subspace. So those TWs are linearly independent and span the range of T, which now allows us to say that these T W sub j's are a basis of the range of T. And how do we now determine the dimension of the range of T if we have a basis? If we have these vectors that I now hand you, I say, here's your package of basis vectors. What's the dimension of the range space? What would you do? You'd start pulling those out of the bag that I handed them in and count them, right? You would say, here's 1, here's 2, here's 3, and how many did we start with? We started with, it's buried somewhere in here, but we started with Nevada of those, didn't we? N of those vectors. We now know then that the list, which by definition a list is finite, a list of these TW sub j's is of length n, and consequently we now know the dimension of the range of T is that value, n. And that's what we wanted to show. We wanted to show that the dimension of the range of T was actually equal to n, and now we can say that therefore the dimension of V, we can write down our final statement that we needed to show, is equal to the dimension of the null space of T plus the dimension of the range of T. And that was because this guy was n plus m, this was m, and that was n. And that's what we were trying to show. Questions on that? And that actually allows us to buy quite a bit of information in working problems. for example. If somebody now gives you a matrix and they start telling you certain things, if they tell you the dimension of the null space, you can see from that matrix by the number of columns in that matrix, you know the dimension of the domain, V. If they tell you the dimension of the null space, now you know the rank of that transformation or the dimension of the range space. How many or what kind of a size can you reach from that linear map, from the domain into the codomain? Is it going to cover the entire codomain? Is it surjective or not? And you'll have to know that from the size of the codomain. We can now write down some corollaries based on this theorem, theorem 3.4. The first one is corollary 3.5. And that now says that no linear map from a finite dimensional vector space, an FDVS, to a smaller vector space, so that's in terms of its dimension. No linear map from a finite dimensional vector space to a smaller one can be fill in the blank. So now we're going from a large domain into a smaller codomain. Is this, to fill in the blank, I'll give you two options, injective or surjective. So no linear map from a large dimensional space to a smaller space can be, so now you're going from something big into something small. You have more opportunity to fill up that smaller one, right? And maybe you can go from many different places in the big one and get to the same point in the small one, right? Which means that it's not going to be injective, is it? So no linear map from a finite dimensional vector space can be injective if you're going from a big space to a little space. Or stated another way, you have fewer vectors in the output space, and in fact, some input vectors must produce the same output. Or in terms of a picture, let's say here is our dimension V, and now we have dimension W is small. There's big, there's small. And they're being mapped by some linear map T. So now we have T mapping to W. What are we saying? we're saying that we actually might be able to find, and what does that red shape now say? Or what is that representative of? Well, maybe it's not very clear, but you could sort of think of that representing the null space. Now you have a non-trivial null space. If you do, then you can create many different vectors. So now in here you have vectors that are adding together with vectors from the null space, and those could then map to the same point in W. So this is trying to show you that the proof of this corollary really says that you have a non-trivial or a non-empty null space. You don't have the zero vector mapping to the zero vector. You can now, and that's our earlier example that we started with. Remember, we found a V1 and a V2 that both map to the same W. And V1 and V2 were not the same. So you could think of V1 and V2 mapping over to W sub 1. So you're going, but the earlier example really didn't have this. So this is not the picture from the earlier example, because the picture from the earlier example was a small domain into a huge codomain, wasn't it? And so in that case, you really can't make this claim as immediate. But in this case, you can say if you have a map from a big V to a small w, there's no way that can be an injective map immediately. You can just make that claim. All right, the other corollary is obviously related to surjective maps. And it says no linear map from a finite dimensional vector space now we're going from small to big to a bigger one. Again, we're saying small and big in terms of dimension. And now you better get this one right. No linear map can be, if it's going from small to big, it can't be surjective, can it? The picture now is you have some small, or let's say dimension V is small, and the dimension of W is big. And now you can't hope to fill that space up. Sort of saying you have a small volume, you can't fill this large volume from the small volume. So you can't cover, you can't go onto that entire space. That's what this one is saying. And that one may be easier to sort of see than the other one, potentially. This is now saying that you have fewer vectors in the input space, and consequently you can't produce all vectors in the output space. Yes? So the big and the small are in relation. The question was, what is big and small, and what are they related to? So it's related to the size of these vector spaces, domain and codomain, relative to their dimension. So the size, small and big, is relative to, if you have numbers for their dimension, then the dimension of the domain is small relative to the dimension of the codomain. So this could say R2 to R7. So if you're going from something R2 with a linear map into R7, you know it can't be a surjective map. Boom, you know that. You don't even have to go any farther. All you have to do is look at the size of those domain and codomain, and you can say, you want to know what? Is it surjective? No. End of discussion, because you can say corollary, what was it? 3,6. That's correct. The small and big could be something as small as 1. Okay? You could go from 2 to 3. You could go from 1 to 2, and that's the difference in small and big. That's all you have to make as far as a change, is 1. And that's this distinction between small and big. So the small and big is relative. It doesn't mean that it has to be 10 bigger. No, it just has to be 1 bigger. And then you can make these claims. In this case, we have that the range of T does not span W. That's really what something being not surjective means. And this is our codomain, or W really is our codomain. And you could see the proofs of that. We just sort of drew pictures and colored. But the proofs you can see in the textbook. Okay, we won't go through those. But those are corollaries from theorem 3.4. It was 2 before 3.6 corollary, right? So the theorem was 3.4, and based on that theorem, you can now make these corollaries. And if somebody asks you now, is this map injective, the first thing you might want to do is compare domain and codomain and their sizes. If they're different, now you go, okay, is one bigger than the other? And what's the point there? Now, if your domain is big relative to your codomain, it's not injective. Likewise for this one. If you start small and go big, you can't cover the entire big, so it's not surjective. Okay? Now let's go to something concrete, maybe. And that's the matrix representation of all of these ideas, these linear maps. Let's now look at, and this should just be a confirmation of what you already know, okay? That we can add matrices, we can multiply matrices, we can scale them with a scalar, we can multiply a matrix times a vector. All of those ideas, that's what we're going to sort of talk about. And some we're just going to quickly just state. But that's what we want to talk about now, is just to remind ourselves that these linear maps can be something that we're very familiar with, which are matrices. And this is now the matrix representation of a linear map. And so if you start to get confused, which that's the whole point of what I'm doing now, is I'm going to try to confuse you, you're going to go, when did matrices get so confusing? It's because now we can talk about these in terms of different bases. I could now have my domain with some basis that may not be the standard basis. What's he doing? And I might have the codomain being something other than the standard basis. And then you're going, what? What's this matrix? Well, just go back to the standard basis and say, well, really, he's just kind of playing with things to make it difficult. Okay? So that's what I want to say first. Well, no, let's see what we can do and just create a matrix first. So let's say we're given a map. And our notation is to say that T is contained in this set of linear maps from V to W. And now let's select, or just say that we have two different bases. V1, V2, how big do I want to say these are? Let me say we have N, Nevada, for the size, dimension of our domain, and that's on V. And let's say that we have W1, W2, Michigan basis vectors on W. And those don't have to be the standard basis. That's what could make this kind of weird. Okay? So V1 could be 101 if it was coming from R3. And you know how to build a basis, right? What's a basis need? What's a set of basis vectors need to be a basis? Two things, right? They have to be linearly independent, don't they? So if I have a three-dimensional space and I give you four vectors, is that a basis? No, you can immediately say no, right? I give you three, and if they were linearly dependent, that wouldn't be a basis either, would it? So they have to be linearly independent, and they have to span the space. So those are the two things. So as long as these V's up to Nevada and W's up to Michigan, depending on what those sizes are, they have to be linearly independent and they have to span that space. That's all they have to be for a basis set. They don't have to be the standard basis. But if you get confused, just draw an example from the standard basis. V1, if let's say V was R4, then V1 would be 1, 0, 0, 0. V2 would be 0, 1, 0, 0, etc. You'd have four of those, wouldn't you? And if Michigan was 6 dimensionally, then W1 would be 1 with 5 zeros. W6 would be 5 zeros and then a 1. And those would be your standard basis. And that's sort of what you're used to seeing or thinking about. Let's just talk in general, though, now. What we want to say now is the action. Again, we have a linear map between these two, a domain and a codomain. And we have a linear map between those. The action of the map, the linear map, the action of the map on the kth basis vector V sub k is going to be written in terms of the basis vectors of our codomain. What? I'm saying that there's our linear map T, and it's operating on our, I can't make K's, so you can clean your notes up better than I can. I never could make a K. All right, so there's V of K. That's the kth basis vector in V, And we're operating on that through this linear map, but that means we're going into the codomain, which says that whatever this resulting vector ends up being, it better be a linear combination of the w's. Correct? And now I have to just go a little bit fancy with the way I label these combinations, because how many of these TV sub k's do I have? Now I have to remember Nevada and Michigan. I have Nevada of those, don't I? I have N of those. And I have Michigan basis vectors in the codomain. So I need to take W1, W2, up to W sub M of those, and now I need to add those up. And I'm going to scale those or combine those with the following notation. I'm going to say that that's A sub 1 comma K. I'm going to double subscript those coefficients. Those are just scalars from the field F, aren't they? And this K then says, oh, this is the coefficient associated with the kth basis vector in the domain. And likewise, this is going to be A sub 2 comma K. And this one A sub M comma K. So I'm going to have Michigan linear combinations of the W's, and I've simply subscripted them this way because I want W1 scaled by some coefficient, A1, W2 by A2, but I need to kind of keep track that I'm going to have Michigan combinations for each of the Nevada V sub K's. So I have to kind of keep track of each of those V sub K's, and that's the reason for the second subscript on the A's. Now, these coefficients, the A sub K's, or A sub double subscripted K's, for all the N vectors V sub K, we can actually put all of those together. They can be collected in the M by N matrix. Meaning, well, maybe I scrolled, you can sort of see what I want to do, I hope. What I want to do now is K is keeping track of the column that it's in. And the first subscript is actually keeping track of the row in this matrix. These coefficients right here are all going to go in the kth column of this matrix. If I said, let's just start at the beginning. Let's start with the first vector V sub 1. That would be TV sub 1, and now this would be A1, 1, wouldn't it? Well, that seems to make sense. It'll go there. This one, A2, 1. It's going to go right below it. And I'm going to have Michigan of those, and that's going to form my first column in this matrix. And that's going to be the linear combination of my basis vectors in the codomain. Meaning now I can say here's A1, 1, A2, 1, all the way down to A sub M, 1. And then I'm going to go over to the generic location of the K. Yes? Okay, so you can wait. You think it'll wait? Let's say that this is now A sub 1, K. This is A sub 2, K. And this is now A sub M, K. And we just continue to do that for Nevada columns. We now have A sub 1 n, A sub 2 n, or row 2 column n, all the way down to A sub m n. And these columns, if you sort of restrict yourself to those, this is really a way to express the linear combination of basis vectors in the codomain, what TV sub n looks like is this linear combination. So this first one, A1n, would scale W1. A2n would scale W2. Is that clear? And this now represents this mapping between the domain and the codomain. And that forms a matrix like you're used to seeing, if this is now an M by N matrix. Question? I can try, but you've seen I've had trouble. So now what I'm trying to say is we're mapping between the domain, capital V, and the codomain, capital W. Now what we want to do is, it's efficient, if we have a basis in our domain, why don't we just look at how each of those basis vectors gets mapped into the codomain? That's an efficient way to find another set of vectors in your codomain. So we take our linear map T and we work on each of these Nevada vectors, basis vectors in our domain, capital V. This then, if you sort of go back to what we've done before, that would say, oh, plug in this, let's go way back to the beginning. Here's a good example. What is capital V dimensionally? What is capital V in this example? And if I scroll up just a little bit more, right, it's R3, isn't it? So we have a three-dimensional V. And that's what we were saying our basis vectors were coming from for V. In this case, we could say, oh, we need 3 of these in the standard basis. 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then we would plug those in to this, and that would give us a representation of T V sub 1. And that would be these A's that we were stacking up. Okay, so this is really just saying I have some vector in your codomain. Well, if you have a generic vector in the codomain, that has to be writable or expressible as a linear combination of the basis vectors in the codomain, and that's what the W's were. So now I'm just saying, what did TV1 give me? Oh, it gave me this vector. Well, I can find the coefficients A subs that will scale these basis vectors in W to produce that TV1. Then I can say, okay, what's TV2? And you can find how it would look in terms of the W's. So that, let's see if we, well, wow. Let me look at an example, and then I'll go back. How about we talk about an example, because that might help make these a little bit more concrete. Let's look at an example first. And maybe it won't make it better, but suppose we go back to this basis changing idea where now we've used before, and I think it's in the book. Suppose our linear map is between a domain that's of dimension 3 and a codomain that's of dimension 2. And this is now a dimension reducing or a dimension changing linear map. And the linear map now is, let's say it's 2x minus y plus 3z and 7x plus 5y minus 6z. So now we're going from a three-dimensional space to a two-dimensional space by this choice of a linear map. And let's just, to be clear, let's just pick the standard basis. Let's say that a basis for the domain, let's just say is our standard basis, V1, V2, and V sub 3. Okay? And let's say our basis for the codomain let's just make that the standard basis. Let's say that W1, what would that be? It's too long, TWO wide, isn't it? It's two-dimensional, it's 1, 0, and W sub 2 is 0, 1. Now, let's see what happens when we what is TV1? Is it clear what I'm asking you to do? Now I just need you to go up here to T and plug in V sub 1 for X, Y, and Z. And V sub 1 was 1, 0, 0. X is 1, Y is 0, Z is 0. So we come over here with those y, X, Y's, and Z's, and that builds up a 2 vector. And that 2 vector for V1 will be, just forget the Y's and the Z's, those are 0, and it will give me 2 times 1, 2, comma, 7. And that's in the standard basis, isn't it? W1 is in the standard basis. Meaning now, if I wanted to build up that matrix with TV1, now I have V1 is equal to this 1, 0, 0. That means that TV1 is going to be 2 times 1, which was 2, and 7 times 1, which was 7. Is it clear where that came from? And what is that actually equal to in terms of our standard basis in the codomain? That should just be 2 times 1, 0 plus 7 times 0, 1. That's our standard basis, isn't it? And that's now just 2 times W1 plus 7 times W2. So this TV1 is A11 W1 plus A21 W2. This is our first column in the matrix. This now says that our matrix is 2, 7 in terms of, and we're going to call this matrix script M of, boy, that's an ugly M, isn't it? Don't tell my writing teacher that I can't write. M of T is now 2, 7. That's the first column. What's going to be the second column? This was TV1 written in terms of the standard basis for W, which was W1, W2. TV2 is the second column, isn't it? And V2 we just need to go back here, whoops, and say, what are we doing? Just replace y with 1 and x and z are zeroed out. Now we have -1 and 5, don't we? So this is now -1 and 5. And what's the last column? We just set z equal to 0, or z equal to 1, don't we? And x and y are 0, so this gives us 3 minus 6. Now here's the kicker, and I'll leave this for you to figure out on your own. What would m of t equal if we changed our basis vectors in W? What if W1 bar was not the standard basis, but was, let's say, 1, 1, and W sub 2 bar was actually, let's say, -1, 1? Is that a basis for 1? Are they linearly independent? Can you find an x, well, that's maybe a poor choice, an a and a b, a plus, or a times W1 plus b times W2, can you find non-zero a and b such that that linear combination equals 0? No, those vectors are linearly independent, aren't they? And they span all of R2. So that is a basis set. Now what I want you to do is figure out what the matrix with that choice of basis, V's are the standard, the W's have now been changed. You now need to figure out what does sort of 2, 7 look like in terms of W1 bar and W2 bar. We're out of time, so you'll have to do that before Monday. Okay? Thank you for allowing me to go over.